Okay, we are working on 4.1 and this is day 2. We're going to look at elimination method today as well as graphing calculator. So let's get rolling. The elimination method. When does elimination method work best? Well, elimination method will work really well when we can eliminate a variable completely. So either I can eliminate x or I can eliminate y. You need to have your equations in standard form for this. When equations are in standard form, and we know what that looks like. That's that ax plus by equals c model. So we've got ax, by, c. So both of my equations 1 and 2 here are sitting in standard form. We want to eliminate a variable. And we do this through, we can use addition to eliminate a variable. Okay, so that's the main idea. And I look at this equation here, and I just want to do a quick thing here, see if I can snap a picture of this. And we want to put this, well, that'll work. So here's the equation set. And what I'm noticing is if I add, those two are going to eliminate right away, aren't they? So let's go through with this process and do our addition. So I am going to add the two equations together. When I do that, I get a 0 x's. I get 5y equals -5. Divide by 5 on both sides, and we come in with y equals -1. Now I need to go find, that was pretty easy, wasn't it? And really set up nicely for elimination since those two were opposite values. They eliminated the x's. Now let's find our x, because we know y equals -1. So to find x, I'm going to take either equation 1 or equation 2. I'm liking equation 2 because it's all positive. So I have 2x plus 2 times -1 equals 5. That means 2x minus 2 equals 5. And then add 2 to both sides. I have 2x equals 7. Divide by 2 and we get x equals 7/2. We have our solution set, right? So I write my solution as an ordered pair of 7/2, or you could say 3.5, -1. Very nice. Next example is example number 6. It says solve this equation, 2x plus 3y. This time I notice that there are 3x, we need to, I was going to highlight this, and then I noticed this second equation isn't in standard form, is it? So let's put it in standard form first, and then see what we can deal with. So standard form is going to be our first order of business. Standard form. I like x's to lead me off, so I'm going to put 2x plus 3y equals 19, and then I'm going to flip-flop the order here. 3x minus 7y equals -6. Now, unlike last time, if I were to go and add these together, I would not eliminate anything, would I? It would look something like that. And that's not super helpful. I guess that'd be a negative. That's not going to be helpful to us. So we can do modifications on this, though. And what I would like to do is maybe take advantage of the fact that I've got a positive and a negative already built in. They will eliminate once I get these numbers to be the same. How can I get those numbers to be the same? Well, as long as we do the same thing to both sides of my equation, I'm going to be fine. So I'm going to multiply the first equation by 7. That'll give me a 21y. And I'm going to multiply my second equation by a 3. So here's what's going to happen. We're going to get 14x plus 21y equals 7 times 19 is 133. Multiplying through by 3 on the next one, we would have 9x minus 21. That's nice because look at that column. And then 3 times 6 is negative 18. Let's go through and add these equations together because we can see we're going to get elimination. That's going to go to 0, isn't it? I get 14 plus 9 is 23x equals 115. Divide both sides by 23. Believe it or not, 23 goes in there nicely, and we get x equals 5. Okay, step 1 is done. We got half of our solution. We got x equals 5. Now let's go find. We have x, so let's find y. And we know that x is 5. Equation 1 or equation 2, which one do you want to take it in to solve? I'm kind of loving equation 1. Once again, all positives, so I'm going to stick with my positives. Sorry, that bounced back. So I'm going to go, would it just hold still? Okay, so we're going to go 2 times our 5 plus 3y equals 19. Well, that makes 10 plus 3y equals 19. Subtract 10. 3y equals 9. Therefore, y is 3. Join our two solutions, and we have the ordered pair 5, 3. Of course, we could check our answers, just like we did on day 1 where they gave us solution pairs. Check out, does 5, 3 work in each of those equations? You should find that they do. Okay, example 7. These are some special cases. 7, 8, and 9 are all kind of special cases, so watch what happens here. Solve the equation. Well, just glancing it over, if I multiplied by 4 here, I could create an 8, and 8 with negative 8 would eliminate. So I think that's what I'm going to do. I'm going to take equation 1 and multiply it by 4. And that equation looks like 2x plus y equals 6. And the second equation, I am not going to modify at all because I'm after that 8, negative 8 combination. Okay, so this equation will transform into 8x plus 4y equals 24. No modification on equation 2, so we just simply rewrite. Oops. And then I'm going to add vertically, and I'm going to get 0 plus 0 equals 0. Oh, interesting. 0 equals 0. This means that I have infinite solutions. There are many solutions that work on this. This is an inconsistent, no, it's a consistent because we have solutions. It is a consistent equation, a consistent system, and they are dependent. Dependent solutions. They're dependent that they're on that particular line. So when I select an x and a y, let's say I chose 0 for x. Well, that's going to zero that out. Then y would have to be 6. And I'd have one of my solutions. Or I could select x to be 1. Now I've got 2, subtract 2 from each side, and I'd come up with 4. So there's just oodles and oodles of solutions, but they would have to fall on this line. You may have also noticed that these two equations looked extremely the same. I just need to multiply the first equation or the second equation by a negative, and now you can see that they are identical equations. And that's why they're consistent but dependent. All right, example 8, another special case. I'm thinking let's multiply the first equation by -2, okay? And then no modifications on the second equation. That'll produce a -8 on top with a +8 down below, and they'll eliminate. So I'm going to get -8x plus 6y equals -16. Copy second equation. Let's add them together. 0, 0. I get 0 equals -2. Not equal, is it? This is not a true statement, and therefore there are no solutions. Penmanship doesn't look very good today. Not a true statement. There are no solutions. And that happens when we have an inconsistent system of equations. Yeah, they almost were the same until they weren't, and therefore no solutions. Special cases of linear systems, if both variables eliminate when a system of equations is solved, there are infinitely many solutions if the resulting statement is true. But if that resulting statement is false, like in our last example, there are no solutions. Example 9 says, use a graphing calculator to solve the system. So you dig out your graphing calculator. I got mine. And, and here we go. So use a graphing calculator and solve the equation. What I want you to do, you were probably at your home screen like that. Hit your y equals key. Let's key in the equation. Oh, but we got to have it for y equals, don't we? So let's transfer this over. Let's solve for y. So I'm going to subtract 2x and get the equation y equals -2x minus 5. And then also, let's add x. So I'm going to have 3y equals x plus 6. And then we need to divide by 3. So I'm going to get y equals 1/3 x plus 2. So there are the same two equations, just modified so that it's y equals. Now let's key that in. So I'm going to have -2x minus 5. And on the other one, I'm going to have 1/3 x plus 2. And I want to graph that. I'm going to hit zoom 6, which is a standard window that's -10 by 10 and -10 by 10 in the y-axis. Ooh, did you see that they intersect? They do intersect. So you know what? Let's just give ourselves a quick picture on this. I'd like a different color here. Right there. I don't know what I grabbed, but I grabbed something. We have one equation kind of coming through here, and the other equation kind of coming through there. And we have that spot that's the same. It kind of looks like 1, 2, 3, like -3, 1. And I could plug that into the first two equations and see if it works. I also could do second calculate or second trace, which gets me into the calculate menu. And I'm looking for the intersection. So I'm going to hit enter. Notice it says up in the top left of our screen, it says equation y sub 1. I'm going to hit enter. And then it again changes to y sub 2, the red equation. I'm going to hit enter. And it's asking me to guess So I'm going to bring this closer and try to get, about on top of it. And there it gives us, the intersection is negative, whoops, lost my graph, negative 3, 1. And I meant to have that screen, but negative 3, 1 is where they intersected. So you can also use graphing calculators to do that handy work. Now, your homework for the day is page 180. You're just doing evens, so make sure you know that. Otherwise, you're going to be doing a lot of extra work that you don't need to. If a system of equation is inconsistent, state the fact. That would mean that I ended up with like a not true statement, like 0 is not equal to, would we have 3 or negative 3 or something in ours. A dependent is when we hit 0 equals 0, and that has many solutions. Okay, so you could hit some of those on these practice problems, and there is the rest of it. Okay, have a great day.